Hey, welcome to Math Life Balance and to a new episode in the series K-Theory Wonderland. Today, I want to tell you about an article that we wrote only a few months ago. This article is called P-Perfection and Group Completion of E-Infinity Monoids, and it's joint work with my friend Maxim Ramsey. Now, what I want to demonstrate today is that just the few videos that I made about K-theory before are enough to explain the main result of this article. Frankly, our research field is so abstract and requires so much background that often it is really hard to explain even the main result. Because to explain why a math result is interesting, you need to explain the context in which this result is surprising or desired. But luckily, in this case, the context was already explained in my introductory videos from negative numbers to K-theory and the magic of group completion, and in the other video, how to make chaos. If you're new to K-theory, watch these videos first. As we discussed in those videos, the process of getting integers out of natural numbers can be generalized to a set with an operation or even a space with an operation. It's called group completion and denoted like this. You take this set or space with an operation and you get a group completion of this set or a space. And we saw very interesting examples of this operation. We saw that if you take finite sets, you get a space which encodes all the stable homotopy groups of spheres. And we saw that if you take finitely generated projective modules over a certain ring, then you get the K-theory space of that ring. So we saw that many very rich examples of invariance appear as group completions of some rather easy to describe spaces. Overall, we saw that it is very often the case that the space is rather simple. So in this example, the spaces are graphs. However, the group completions are very, very difficult. They can have all higher homotopy groups non-trivial. And this is the context in which our result that we prove in our paper is surprising. Roughly what we show that the situation changes completely after you invert a prime number p. So let's pick a prime number p, and then on our space with an operation, we have the map multiplication by p, also called the Frobenius map, which sends every element to itself added p times. This is a generalization of usual multiplication by p on natural numbers. Say we want to invert a prime number p. On natural numbers, it's easy, it's familiar. You say that inverting p on natural numbers is considering all natural numbers divided by p and its powers. A similar operation you can do on spaces too. So basically it means to force the operation of multiplying by p invertible. So it is denoted m with p inverted, and on pi 0 this is the same operation like here. So it is inverting p in this discrete sense, like with natural numbers. But on higher homotopy groups, this operation is quite mysterious, and we will see now how much. So the main theorem that we prove roughly says the following. Let M be a nice space, which is a monoid, commutative monoid. An example of such is the finite sets that we saw, and for example, the space of projective modules over a nice ring. Then the operation, the group completion operation from M to MGP, after you invert P, becomes an embedding of positive components. So what does it mean? Although M and M group complete had completely different homotopy types, so this could be very simple, whereas this could be extremely difficult, after you invert P, they become of similar complexity. Components of this guy become components of this guy. Well, there is a subtlety at 0, that's why I say positive components. So at 0 here, there can still be no interesting loops, whereas here they can be interesting. But all the other components are literally components of this guy are components here. Why did I have to explain all these complicated things about group completion of spaces in previous videos, and why do I use it in these videos? It's because it's not a discrete phenomenon. Because if you look just at natural numbers that go to integers, yes, of course, if you invert p, then natural numbers with p inverted are the components of integers with p inverted. These are just points. There is no interesting homotopy theory going on. So this theorem is not a discrete phenomenon, and that's why we need to talk about spaces. So that's an explanation to why we need homotopy theory. And so the moral is that we knew before that group completion is very hard, but now we know that inverting p is also very hard. Thank you for listening. Bye-bye.